When we're dealing with sets, we can't use the typical addition, subtraction, multiplication, and division because, well, I don't even know what those would mean. Instead, we use different operations. So if we want to take two sets and combine them together in various ways, or even one set and do something with a complement down there, if we want to take sets and do things with them, we need to use these various set operations. The first operation we see is called an intersection. And if you think about intersections where we use this word in real life, let's say we have two streets. We have Arthur and we have Beckwith. So Arthur, the street of Arthur is all of this stuff. The street of Beckwith is all of this stuff. When we're talking about the intersection of Arthur and Beckwith, that is the overlapping region between them. And that's actually a very good way to describe the intersection of two sets. So if we had, let's say A was the set 1, 2, 3, 4, and B is the set 1, 3, 5, 7, then the intersection of these two, written like this, A intersect B, this is sometimes called a cap versus a cup down here that we're about to see, but in any case, A intersect B, this is going to be all of the things that are in common. So this would be 1 and a 3. Those are the only two elements that are in common between these two sets. So the intersection of those would be the elements 1 and 3. So a union is kind of the counterpart to an intersection. If we were thinking of our street analogy here, this is Arthur, this is Beckwith. The union of these two streets would be, well, not just the intersection, it would be everything that's in either A or B. So this is in A and in B. Over here, this would be in A or in B. And oftentimes when you're reading through word problems and whatnot, you can search for, if you're being more restrictive, if it has to be both in the first thing and in the second thing, generally you're talking about an intersection. If it can be in either one of them and it's in the thing you're talking about, then you're probably talking about a union. So if it's in A or it's in B, or both, sometimes you add on the or both. You don't always add on the or both there. But so for instance, you can see here I don't say or both, because if it's in both A and B, then it's in A, and then this thing is true. So in any case, let's do the A and the B that I defined up there, A union B. If we have 1, 2, 3, 4, and 1, 3, 5, 7, then A union B would be everything that's in either of them. So 1, 2, 3, 4, 5, 7. That would be A union B. So intersections versus unions. One thing that you'll note when you're talking about intersections, these tend to shrink, to be smaller. An intersection tends to involve fewer things. You can see we have 4, n of A was 4, n of B was 4, n of A intersect B is only 2. Versus down here, n of A union B, this tends to grow. N of A union B was actually 6 different things. So an intersection tends to be more restrictive. It's exclusive. It throws things out. One way to think of an intersection is to start off with all the elements in A and then throw out anything that's not in B. So this would be one way. This is actually a way that I tend to suggest approaching it. If you start off with all of A, then you look through B and you say, okay, well, 2 is not in there and 4 is not in there, so that means we're only left with 1 and 3. Versus a union, you'd start off with all of A, then you'd say, okay, well, I know all of A is in the union. I'm also going to look at B and say, well, 5 and 7 should also end up being in there. And so that's actually how I recommend approaching unions. So getting rid of things is intersections, adding them in is unions. A complement in order to do a complement, we need to define what's called a universal set. And the universal set kind of gives us some overall scope. Let's say with the A and B I had defined up there, let's say U is all digits. If you don't know what I mean by all digits, I'm talking about 0, 1, 2, 3, all the way up through 9. So, yeah, those are the digits. There's 10 digits. If you were to count them up, you'd see that there's 10 of them. So, let's see, how did I define A? A was 1, 2, 3, 4. If I defined U in this way and A in this way, then that means A complement. This is going to be everything that's not in A. We need to have a universal set because, if I described all numbers that are not in A, well, that's kind of a big list. But even then, I'm kind of implying that U would be all numbers. However, I've restricted U here to be just the 10 digits. And so when we're talking about the complement of A, well, 0 would be in there, but not 1, 2, 3, or 4. 5, 6, 7, 8, and 9 would also be in there. So A complement, this is everything that's not in A, but again, in order to talk about everything that's not in A, you have to have some sort of upper limit, because sets really could be talking about anything. I could have letters in there. I could have words. I could have, anything I really wanted to, and so U gives us some sort of limitation.